Ladies and gentlemen, good afternoon and welcome to our webinar today. I am Dr. Wenchao Xue and the Director of the Asian Institute of Technology, Belt and Road Research Center. So today is the second day of our DIBA Expert Talk series on Big Earth data for the Sustainable Development Goals. And we are going to spend the next 2 hours to discuss about two more concerned SDG goals, SDG 14 and also SDG 11. Starting from SDG 14, this SDG aims to conserve and sustainably use the oceans, seas, and marine resources for sustainable development. This is a very important SDG for the Southeast Asian countries such as Thailand, as there are enormous marine resources in this region, because we have two oceans, the Pacific Ocean and the Indian Oceans here. So today we are very happy to invite Dr. Haifeng Gu as our first speaker to share his experience and also some research related to the application of Earth observation technology for coastal environmental monitoring and assessment. So before we start today's lecture, allow me to give a brief introduction of our speaker. Dr. Haifeng Gu is a senior researcher in the 3rd Institute of Oceanography, Ministry of Natural Resources of China. He obtained a PhD degree on ecology from the Ocean University of China in 2007. His main research interests include the harmful algae blooms, the ecological consequence of eutrophication, and the taxonomy of harmful microalgae. He has published more than 100 research papers in international journals, and now he is serving the editorial board of Harmful Algae and the Journal of Applied Oceanography. So may I have the pleasure to invite Professor Gu to provide his lecture today. Professor Gu, please.
I'm very pleased to have the opportunity to introduce our work in the South China Sea during past years. I'm also happy to share my experience and ideas with you. My presentation is about eutrophication assessment in the South China Sea and its ecological consequence, focusing on the response of phytoplankton. My presentation includes 4 parts. The background will introduce global eutrophication, its formation mechanism, and subsequent hypoxia. In the eutrophication assessment, I will introduce a new method to evaluate eutrophication in the South China Sea based on dissolved inorganic nitrogen, dissolved inorganic phosphorus, and dissolved oxygen. Then I will report a case study in the Gulf of Thailand about consequence of phytoplankton composition to eutrophication, focusing on harmful microalgae. In addition to eutrophication, global warming also had a profound effect on the marine ecosystem. Finally, I will go back to the South China Sea to see the distribution of harmful microalgae at a broader scale, covering both eutrophic and oligotrophic areas, and both tropic and subtropic areas. So from the left map, we can see yellow points representing eutrophic areas are distributed worldwide. Eutrophication is often accompanied by hypoxia, as indicated by the red spots. The right figure shows the effects of anthropogenic nutrient enrichment, including urban runoff, agriculture and livestock runoff, and resident runoff. These excessive nitrogen and phosphorus discharge will promote the growth of microalgae and even lead to bloom outbreak. These microalgae cells will quickly use up the nutrients, followed by bloom decline. These dead cells will settle down to the bottom and be decomposed by bacteria. Oxygen is needed during this process, and hypoxia will form subsequently, especially in the estuary where stratification occurs. Blooms due to eutrophication is commonly found in the South China Sea. The upper figure shows an unprecedented large-scale bloom by the Noctiluca sentiments. This is the cell. The bloom was caused by the red Noctiluca sentiments with an area of 6,400 square kilometers. Fortunately, it lasted only 3 days and then disappeared. The lower figures shows high microalgae biomass nearby the Qiang Island in the inner Gulf of Thailand. We can see the colors cannot grow well, as they are covered by the microalgae due to the insufficient light. Manila Bay is a well-known area suffering from eutrophication. In the 1990s, a dinoflagellate Pylodinium is responsible for recurrent blooms in Manila Bay. But then, the bloom species changed, possibly due to the nutrient composition changed. In February 2015, there was a massive unit mortality in Manila Bay. From the figure, we can see numerous fish surface for breathing, so it's safe to conclude that hypoxia might be responsible for the fish loss. Another example of eutrophication is a recent incident in Penang, Malaysia in August 2019. This area is highly populated and suffers from eutrophication. There are a lot of fish cages in a shallow sea area, and the majority of them died due to the hypoxia. The diatom Paloceocilo is responsible for the bloom, and we can see the dissolved oxygen decline to very low, about 2 milligrams per liter in the night, during the night. The hypoxia area was only found near shore, but not in the offshore, about 4 kilometers far away from the coast. So this is a map showing sampling stations in the South China Sea from December 2018 to December 2019. We try to cover the South China Sea, so we choose Beibu Bay and the Gulf of Thailand, Johor Strait, Manila Bay, Lombok of Indonesia, and the Bay of Bengal. Johor Strait is located between Singapore and Johor, Malaysia, and is a well-known eutrophicated area. Manila Bay is also a eutrophicated area, but Lombok is an oligotrophic area. There are diverse approaches to assess eutrophication. However, to date, there is no standard method which is accepted widely. Therefore, eutrophication assessment is classified as Tier 2 according to regulation by IOC with UNESCO. Some people refer to simple eutrophication index involving a few nutrient parameters, but others use the complex index involving a lot of parameters. In this study, we only use 3 chemical data, DIN, DIP, and DO, considering that the former 2 are easy to obtain, and DO is an important indicator for eutrophication, as shown in the previous slides. We also collect biological data by sequencing the eDNA to study the ecological consequence of eutrophication. Here is the results of inorganic nitrogen, the sum of nitrate, and ammonium in 6 study areas. In each area, we collected surface and bottom water samples from at least 10 stations. So these red columns refer to the average values, and the bars represent the standard deviations. So water quality standard in terms of inorganic nitrogen is the same in China and ASEAN countries, indicated by the blue line. So from the figure, we can see that the DIN in Beibu Bay, Johor Strait, and the Bay of Bengal were about 0.2 milligram per liter, and thus exceeded the standard. Here is the results of inorganic phosphorus in 6 study areas. The yellow columns represent the average values, and the bars represent standard deviation. So water quality standard in terms of inorganic phosphorus are different between China and ASEAN countries, as indicated by the 2 blue lines. The reason is that there are 5 grades of water quality standards in China, but only 1 in ASEAN countries. Inorganic phosphorus in Johor Strait, Manila Bay, and the Bay of Bengal exceeded the standard of both China and ASEAN. A normal area has a ratio of nitrogen and phosphorus of 16, and this value was called red field value. So when the ratio is less than 8, phytoplankton growth was limited by nitrogen, and when the ratio was greater than 30, phytoplankton growth was limited by phosphorus. Eutrophication leads to the imbalance of the ratio of nitrogen and phosphorus in seawater, and there must be a relatively surplus of nitrogen for phosphorus limited water body or phosphorus for nitrogen limited water body. The contribution of this relative excess of nutrients to eutrophication can be truly reflected only when the water body is supplemented with the appropriate amount of phosphorus or nitrogen, so that the ratio of nitrogen to phosphorus is close to 16. In 2019, the ratio of nitrogen to phosphorus in the Beibu Bay and the Gulf of Thailand is exceed 30, while the nitrogen to phosphorus ratio of Manila Bay was less than 8, indicate that the sea area was limited by nitrogen, and the other 3 areas had normal nitrogen to phosphorus ratios. The Johor Strait is located between Singapore and Johor of Malaysia and well known for its eutrophication and harmful algae bloom. According to the survey carried out from May 2018 to April 2019, hypoxia was found in the bottom water with an area of 10.3 square kilometers, but not in the up surface water and medium water. Even during our survey in May 2019, we also detected hypoxia in several stations in the bottom water with a value of 2 milligrams per liter. This hypoxia is due to prolonged high biomass diatom blooms as published last year. The same situation exists in Manila Bay. A large area was detected during our survey in December 2019 as shaded by this area. The DO decreased to as low as 0 in the bottom water, and we also found a lot of diatoms, which are probably responsible for hypoxia. Considering that hypoxia is one of the main problems in countries around the Belt and Road, the eutrophication evaluation method select inorganic nutrients as the main parameters and combines the dissolved oxygen index in the secondary ecological response. Inorganic nitrogen and inorganic phosphorus were selected as inorganic nutrients. Compared with inorganic phosphorus, inorganic nitrogen pollution is usually more serious. Therefore, the weight given to inorganic nitrogen was 40%, and inorganic phosphorus and dissolved oxygen accounted for 30% for each. For each parameter, they were quantified with a linear equation. For instance, DIN less than 0.2 milligram per liter will score 40, but only score 0 if it is greater than 1 milligram per liter. So the same situation applies to inorganic phosphorus and DO. The eutrophication indicator established in this case is composed of index corresponding to inorganic nitrogen, inorganic phosphorus, and dissolved oxygen and is divided into 4 grades according to the degree of eutrophication corresponding to different colors. So if the score is between 80 to 100, so the color is green. So in the case study, the eutrophication assessment of 5 sea areas in the South China Sea was performed using the new assessment method. So the left figure showed that the water quality of Beibu Bay, Gulf Thailand, Longbu was very good, while some stations in the Johor Strait and Manila Bay had different degrees of eutrophication. And one station in the Johor Strait has severe eutrophication as indicated in the red. And 3 showed moderate eutrophication as showed the brown, and 2 showed slight and no eutrophication, respectively. 3 stations in Manila Bay showed moderate eutrophication as showed in brown, and 7 showed slight eutrophication as indicated in yellow, and 4 had good water quality as showed in green. So this is the conclusion of this chapter. A eutrophication assessment method suitable for the South China Sea was established based on the comprehensive utilization of inorganic nutrients and dissolved oxygen contents, and considering the status of water nutrient pollution and secondary ecological effects. The newly established eutrophication assessment method was used to evaluate 5 representative sea areas in the South China Sea. The results showed that there were different degrees of eutrophication in the Johor Strait and Manila Bay. These results were published as a case study in the Big O State in support of the SDG in 2020. So I will introduce a case study in the Gulf of Thailand. The harmful blooms are one of the consequences of eutrophication. From the low figure, we can see that the number of HAB events reached a maximum in 2005 and decreased sharply afterwards in Malaysia. However, even the number and the scale of HAB is low, so catastrophic damage to agriculture can be severe. For instance, the bloom by Calodinium austral in Johor Strait in 2014 caused economic loss of several millions dollars. The HAB statistics in the Gulf of Thailand is not available, but at least we are sure HAB is rare in this area, and the most important species may be the red and green Noctiluca cinquillans. However, this does not mean that HAB species are also rare in the Gulf of Thailand. Generally, there are 3 kinds of HABs. The first was caused by species which produce toxin. These toxins are toxic to human beings. The second was caused by species which produce fatty acid-like substance. They are responsible for fish-killing events, but not harmful to humans. The third is caused by non-toxic species, such as diatoms, but will lead to hypoxia. To date, there are two paralytic shellfish toxin-producing species known in the Gulf of Thailand. The first is Alexandria tamiawanichi, and the second is Alexandria minutum. These two species can produce PST toxins. These toxins microalgae will be fed by shellfish, such as oyster, and the toxin will accumulate and transfer to humans. The oyster production in the past decades in Thailand is relatively stable, and divide the production to Thai population, we can conclude that average consumption is very low, about 0.3 kilogram for each person. Such low consumption may decrease the risk of potential food poisoning in Thailand. There is only one food poison due to eating PSP contaminated green mussels in Plant Buri in May 1983. The responsible species was originally identified as Alexandria tamarensis, but later was described as a new species, Alexandria tamiawanichi. Dr. Tamiawanichi is a professor at University of Chulalongkorn and a pioneer in herb research in Thailand. Unfortunately, he died of a car crash during the field survey, so the species is named to honor and memorize him. Alexandria minutum was reported in the Up Gulf of Thailand, but did not cause food poisoning. Both Alexandria tamiawanichi and Alexandria minutum can produce succinct toxin and its analogs, which are voltage-gated sodium channel blocks. In addition to Alexandrian species, two other dinoflagellate species, Pylodinium bahamensis and Gendinium catenatum, are also able to produce PST. These two species have been reported in the eastern part of South China Sea, but whether they are present in the Gulf of Thailand is not clear. There are two important fish-killing genera of dinoflagellates in the South China Sea, Magalophedinium and Calonium. Each genus includes several species. For Magalophedinium, there are two species, Magalophedinium polycricus and Magalophedinium fluorescens. The former species has a wider distribution in the South China Sea, including Gulf of Thailand. But the latter species is rarely reported. Calonia also includes several species. Among them, Calonia mikimoto is a cosmopolitan species, but it has not been reported in Gulf of Thailand. So we can see that there's no record. As many as 26 Pseudonecia species are known to produce the neurotoxin domo acid. Only two toxic Pseudonecia species, Pseudonecia calianthus and Pseudonecia delicatissima, have been reported in the Gulf of Thailand. In contrast, 6 toxic Pseudonecia species have been reported from the Malaysian waters, suggesting that more toxic Pseudonecia species may occur in Gulf of Thailand. So the right figure shows a non-toxic species, Pseudonecia sub-Pacific, reported in Gulf Thailand. Species of Pseudonesia are morphologically very similar, so only detailed study using TEM or molecular sequence can reliably distinguish them. So here is a map showing the sampling stations in the Gulf of Thailand and the Perhentian Island in Malaysia in 2018. So we collect the samples in Chumpong and the Perhentian Island in July and August when southwestern monsoon dominates. So we also collect samples in Trat and Qiang in December when northeast monsoon dominates. From the left figure, we can see that the currents flows from Chumpong to Perhentian. And from the right figure, we can see the current flows from the up Gulf Thailand to Trat. This water exchange may produce high similarity of phytoplankton community. So this is a flowchart showing the details of our work. We collected water samples for eDNA. The previous work on phytoplankton in the Gulf of Thailand is mainly based on light microscope. This method is time-consuming and need experienced experts. High-throughput sequence has been widely used for study prokaryote and eukaryote microorganisms, but such kind of study generally target 18S ribosome DNA. Previous survey using LSU and ITS are rare, although these fragments are more valuable and have high resolution. We also measure the nutrients and the environment facts, including temperature, salinity, chlorophyll A, and turbidity. Finally, we use the canonic correspondence analysis to analyze the relationship between phytoplankton community and the environment. So the up figure shows general trend of nutrients in the 4 areas. The average DIN was highest in Trat, but much lower in other 3 sites. The average phosphate concentration were high in Trat and Qiang, and the average silicate for concentration were high in Qiang and Chumpong, but low in Trat and Perhentian. So the low figures show the general ecosystem in the 4 areas. So Trat Bay, we encounter macroalgae blooms, which were not observed elsewhere, which is consistent with the high DIN and the DIP. In Qiang, the water is turbid and the colors did not glow well. In fact, in the north of Qiang Island, colors cannot glow due to the fresh water runoff by Topaya River in the Upper Gulf. In contrast, the colors in Chumpong are much better, and in Perhentian, the colors are the best. So according to the analysis of similarity based on the LSU sequence, we can conclude that the phytoplankton composition are significantly different among the 4 areas, as the p-value is only 0.001, suggesting the results are reliable. This is consistent with the general trend of the status of coral reef ecosystem. In this study, we also compare the results from the LSU, ITSE, and ITS2. So we can see that a total about 50 dinoflagellate genera and about 72 species were identified. To find the relationship between phytoplankton community and the environment in the Gulf of Thailand, we performed canonical corresponder analysis on the dataset from the LSU sequence. So the green spot represents samples from the Pohentin, and the pale spots, blue spots, represent samples from Chunpong. They are separate from each other and from samples from Qiang and Tlat. And we can see that the samples from Qiang and Tlat group together and they are positively affected by the phosphate. According to the database derived from LSU sequence, we found phytoplankton community are similar at a family level in Gulf of Thailand, but different from Pohentin Island. Diatoms, as represented by the black color, is the dominant group in Gulf of Thailand, followed by the red dinoflagellate. But in Pohentin Island, dinoflagellate is a predominant group with a few diatoms. However, phytoplankton are significantly different at the genus level. The two diatom genera, as represent the black is Pseudonesia and the red is Cheetah. Cheetah colors are dominant in the Gulf of Thailand, but the relatively abundance change in different areas. In Pohentin Island, the two dinoflagellate genera, Protoploidinium and Scribacillo, dominate the groups. Some Pseudonesia species are able to produce dominant acid, which can be transferred to fish or shellfish. And they are considered the cause of whale strangling, as dominant acid was detected from the flesh of stranded whale. 5 potentially toxic Pseudonesia species were detected, as well as 14 non-toxic Pseudonesia species in the 4 areas. Pseudonesia america and Pseudonesia brasila could not be differentiated based on the LSU sequence. So is the case of Pseudonesia simulans and Pseudonesia delicans. The relative percentage of toxic Pseudonesia or total Pseudonesia were high in Tlat Bay, about 68%, followed by Pohentin, about 50%. The highest relative abundance of Pseudonesia galaxy and Pseudonesia multistrata were found in Tlat and Chunpong, the black color. The database based on ITS1 sequence revealed that the dinoflagellate community are similar at a genus level in the Gulf of Thailand, but different from the Pohentin Island. The dominant genus is Gyrodinium, as indicated by the black color, followed by the red Alexandrian. Gyrodinium is a heterotrophic genus and mainly feed on diatoms, which is consistent with the fact that the diatom is a dominant group in the Gulf of Thailand. 11 harmful dinoflagellate species were recovered with relatively high abundance based on the dataset derived from ITS1 sequence. These include Alexandria tamiranici, the previously known toxic species in the Gulf of Thailand. Alexandria flaggi, which is a PSP-producing species and has never been reported in the South China Sea. Alexandria pseudogonolax, Azadine poplin, and many other species. Most of them have never been reported in Gulf Thailand, even in the South China Sea. Alexandrian pseudogomelax, Alexandrian tabaranici, and Calodinium austral were the dominant species. So here's the conclusion. 5 potentially toxic pseudonecia species were detected, with 4 as newly recorded species. 3 paleolithic shellfish toxin-produced dinoflagellate species were detected: Alexandria tamiranici, Alexandria flaggi, and Gendinium catenatum. 2 Azaspilid producing dinoflagellate species, Azadinium poplin, Azadinium spinosum, and a pinotoxin producing species, Volcanodinium rugosum, were revealed from the dataset. 6 fish-killing species were detected, and all representing new records in this area. These results were published in the International Journal Haifeng this year. So the last part is a case study in the South China Sea. For the last part, we go back to the South China Sea and report an ongoing study focusing on harmful algae. We targeted the ITS-1 region for a more precise understanding of these important species. As previously introduced, there are 3 main species which can produce PST. It's interesting to note that the Paludinium is the only distributed in the east part of South China Sea, and at that time, only 2 Alexandria species, Alexandria tamiranici and Alexandria magnetum, are reported. So 10 years later, in the updated maps, Paludinium is still only distributed in the east part of South China Sea. And the records of Gendinium catenatum in the Gulf Thailand is still rare. So as we know, in addition to eutrophication, warming also has profound effects on the marine ecosystem. Global warming is apparent in the past century due to excessive emission of CO2 in the South China Sea. The surface seawater temperature rises at 0.014 degrees every year. So we have 2 questions. Question 1, is there endemic species in the South China Sea? And the question 2, if yes, are these tropical species moving northward? So this is sampling areas. So we focus recovering the tropical areas and also subtropical areas. And we also collect the samples in nearly the same times from September to November in 2019. So here's the basic preliminary results. 3 pelagic shellfish toxin-producing species were detected: Alexandria tamiranici, Alexandria flaggi, and Gendinium catenatum. So we found that this species, Alexandria flaggi, this species was originally described from Brazil, and it has never been reported in the South China Sea before. And Alexandrium pacificum was previously only reported in the South China Sea, but not in the Gulf of Thailand. Alexandria tamiranici is originally described from Gulf of Thailand, and it has been reported in the Beibu Bay recently. However, its occurrence in the Taiwan Strait has never been reported. whether this is a recent disposal due to warming is an open question. Alexandrian pseudogondolax does not produce PST, but it is able to produce goniodomin A. It has a wider distribution from the temperate area to subtropical areas, but its occurrence in the tropic area has not reported. Here is a finding of Calonia mikimoto and Calonia austria. And here is another two fish-killing species. And here is a record of the first record of Maglophidium fulvescens. And we also detect a toxic Pseudonesia species. So here is a conclusion. Totally, about 15 harmful microalgae were identified using metabucketing targeting ITS1 region, and most of them have not been reported in South China Sea. So based on present study and literature, most harmful macroalgae can adapt from the tropical to temperate areas. There are some endemic in tropical species, whereas whether there are some potential northward dispersal is an urban question. Thanks.
Thank you very much, Professor Gu, for sharing a lot of scientific insight about the eutrophication and also your research output. Especially quite interesting, you shared information of Gulf of Thailand. I think many of our audience are quite interested in this information. And I do see some of the participants actually request to share this slides informations with them. So I hope you could consider that to share this information with our audience. Okay, so we have collected several questions from the audience. Some I think quite close to your lecture. Some are maybe expanding to other interests related to the coastal pollution. So let's try to maybe ask about these questions. So I think firstly, there's a question asking, so you mentioned that there are, okay, so this is one question talking about the plastic. Okay, so we know that the SDG 14 actually in recent year, it increased the more concern on the coastal plastic in addition to the coastal eutrophication issues. Perhaps this is not in your research interest, but would you also like to share some of your ideas whether, say, in the future, we can also adopt the big Earth data to monitor the plastic in the sea, like we are doing now using remote sensing to monitor the eutrophication in the sea. Would you like to share some of your opinion?
Hi.
Yes, yes. Can you?
Yeah. In fact, so there are, I think there are 16 parts in the SDG. So for SDG 14, the topic is life underwater.
Yes.
So in SDG 14, we have a lot of case studies. So one of these studies is on microplastic. So I think we have such report. Maybe next time, I think you can invite the research to give such kind of presentation. I think we already have.
Oh, good, thank you. Very interesting. Actually, I think many of our colleagues here are quite interested in this new issue because we talk about the eutrophication for years, and then these 2-3 years, then the big concern comes with this coastal plastic. So we are also looking forward to have further chances to communicate on this special concern. Okay, so then we move to maybe further questions. Okay, so there is a question. So in your lecture, you have mentioned that in the research, you have detected many toxic species, the microbials in this region, in the coastal areas. And also there is a potential impact caused by the climate change. Okay, so do you think that there will be some significant impact to the fishery in this region, in different countries? And if there could be potential impact, so what do you think the government or the fishery industries or the fishing men, they should know about it or take some countermeasures to manage such kind of a risk?
Yes. So as I introduced previously, there are three kinds of harmful microalgae. The first is toxic to human beings. The second is harmful for agriculture. And the third is not harmful, but they will cause hypoxia. So I think it's very fortunately that there are not many harmful algae blooms outbreak in the Gulf of Thailand. But for the third type, I think there are already some hypoxia in the upper Gulf of Thailand, as there are a lot of freshwater rivers discharge, and they will cause some stratifications. And for Gulf of Thailand, diatom is very abundant. So if the too many diatoms grow, so they will die and settle down, so they will cause hypoxia. I think for Gulf of Thailand, this is the most important problems.
Yeah,
not the harmful species. Yeah.
Okay, thank you very much. Okay, I have also one question from my concern. Could you, I know that there are a lot of research going on in the South China Sea and also by your institute and also under this DBA programs. And could you briefly give us some introduction, like except for this coastal eutrophication studies, what are the major concern the research are going on, like under this SDG 14. So would you mind to give us some brief introduction about the current research that are running on under DBA program? Perhaps, yeah, maybe some of our audience will be have special interest on different topics.
I'm not sure if I catch you rightly, but I can give some introduction. In China, the government asked us to apply for some proposals. So I just introduced one of the proposals. Because in China, the eutrophication is also very severe, and there are many, I think, very severe problems in the ecosystems. For instance, in the Yellow Sea, every year some macroalgae will break out, and there are dense macroalgae will float northward to Qingdao. So they call it a green tide. So this is very important problems in China. So now we are trying to consider that reduce the excessive discharge of nutrients to the sea. So we will model how many nutrients needed to be cut so that the ecosystem will recover. So this is one of the proposals we are just to make. I think maybe helpful for the Southeast Asia countries also, I think.
Yeah, thank you. I think so. We are actually facing the similar problems, and probably the solution will be quite similar too. I just found there is another question from the audience. So you have talked about the nutrients. So this question concern about some hazardous chemicals which has been discharged by different industries. And then the question is, how should we keep safe of our seawater or the coastal environment from this industrial discharge?
I think the most important is the treatment in all the wastewater. I think how to treat the wastewater properly and make them comply with the standard of water quality before they are discharged to the sea. I think this is the most important.
Okay, thank you very much. Thank you, Professor Gu, for your precious time and sharing the knowledge with us, and also answer our questions. So I think I'm going to close this session. Thank you very much again, Professor Gu, for your lecture and the sharing. And for the audience, please don't leave. We are coming back soon with the next lecture, which is regarding to SDG 11 about the sustainable cities and communities. So my colleague, Dr. Aberdeen Vinicon, will moderate the next lecture. Hope you enjoy it. So see you very soon. Thank you. Thank you very much.
Okay, good afternoon, everyone. So welcome to the last session of today's webinar. So this session is about the big Earth data in the support of the urban sustainable development, which is relating to the SDG 11. Even though this is the last session of the webinar, but I think the information that's going to be discussed going to be very interesting, because this one we're talking related to the sustainable city and communities, which is going to be much related to everyone's interest. So let me introduce our speaker, Dr. Qiang. Dr. Yep. Yeah. Good afternoon, Dr. Xing.
Good afternoon. Thank you.
Dr. Xing is the assistant professor at the Aerospace Information Research Institute, Chinese Academy of Science. He mainly engaged in the study of urban sustainability related to the United Nations SDG 11. He has undertaken and participated in more than 10 projects for the National Science Foundation of China, the Young Talents Program of the Chinese Academy of Science, the World Bank, and others. So he has published more than 13 SCI academic papers and participated in writing 6 monographs. So we wish that today's lecture going to be very interesting and also going to be benefit to all of the participants. So again, I would like to remind that if you have any question during the presentation, please type in the chat box. And then at the end of the session, we will have the Q&A session. So Dr. Xing, if you're ready, then the floor is yours. Thank you.
Thank you. So I will share my screen first. So can you see my screen?
Yes.
Okay. I will put it false.
Yep. Yes, please.
Okay. So thank you for AIT colleague, and it's my great honor to be here to make this presentation on behalf of our team in CBARS from Chinese Academy of Sciences. My presentation covers 5 parts: the background and for SDG, and the second is the Cast Earth for SDG 11, which is a big project, I think, in Chinese Academy of Sciences. And the third part is about the SDG 11. One of the indicators belongs to SDG 11.3.1, which is mapping the high resolution global impervious surface area. We call it a high GSA product. The fourth is about using this product and some other data to assessing the urban sustainability in China, and also in one of our demonstration province, Hainan province. The 5 is some conclusions. So as you know, urbanization now yes, plays a very significant role in sustainable development. For China, starting from 1978, our urbanization rate is just 20%, but in 2020, it jumped to 63 or 64 around. And in 2030, we predict it may become to 70%. And you know, this urban area not only produce 80% of economic output, and also 70% of energy consumption and carbon emission. So this is a very important aspect for sustainable development goals. So for SDG 11, in fact, all the SDGs are related, interconnected way. But for SDG 11, we see it relates to slums, air pollution, traffic congestion, or some inadequate freshwater supply, or some industrial waste, or some basic services, and some public spaces are included in SDG 11. So let's come to more detail about these indicators for SDG 11. In fact, it now has 4 indicators belongs to Tier 1, and 10 indicators belongs to Tier 2. The Tier 1 means this classification is from United Nations. It describes the data. For Tier 1, it means it has methodology and also data. But for Tier 2, it means it has a methodology, but still lack of data. So now our work is just to connect us using bigger data technology to develop as much as possible the data and to access the urban sustainability. Another issue, as I mentioned before, is this, in fact, not only SDG 11 related to urban. From the other 16 goals, in fact, it also relates closely to SDG 11. But for some for the 6 entry points, which also proposed by United Nations, it also included and emphasized the urban and the peri-urban development as the one of the 6 entry points, even for the because this 6 entry point is summed from 17 goals, so it still puts urban as this as one of the 6th part. And you see this 6th transformation also closely related to the 17 goals. So the next part, I will come to the second part for Cast Earth project for SDG 11. For our Cast Earth project, we proposed to introduce science and technology to access urban and peri-urban development. We focus on shanty towns, which is called slums in the world, but in China, we normally call it shanty towns, and some public transportation and the urbanization, which relates to land consumption and population consumption. And the fourth is the heritage protection. Then the disasters laws to relate to population and economics, and the urban pollution, which comes from ground, such as the industrial, and also the air pollution, such as the PM 2.5 or PM 10, and the public space in urban areas. And also we make some comprehensive assessment of this SDG 11. So for the first one, we estimate the population living in shanty towns as a percentage of main urban district residents in main cities in China. We normally use the Gaofen second satellite, high resolution satellite imagery, and the deep learning method to extract the urban, the shanty town regions in 27 Chinese cities in 2019. It covered an area of 124 square kilometers, and with a total population of 1 million. So it shows that there were significant differences between eastern and western cities in the ratio of area and population of shanty towns to those of main urban districts. Here, yes, we mainly extract this information from satellite remote sensing. For the next concerns concerning to public transportation in China, we used the 1 kilometer resolution population grid data. By this population data was divided by sex and age for 2015 and 2018, and it shows that the proportions of the population with convenient access to public transportation were 64% in 2015 and jumped to 80% in 2018, because so it shows that China has made significant progress on improving the public transportation in the SDG time period, which starts from 2015. Another aspect is the natural and cultural heritage protection. In fact, we propose to improve the SDG 11.4.1 indicator, increase in capital investment per unit area to protect and safeguard the world's culture and natural heritage. The chart on the left bottom, it shows that the sustainable development of Chinese world heritage was obviously improved from 2006 to 2017. And the chart on the right shows that the average of proposed urbanization intensity indicator covers 79 world cultural heritage sites in the Belt and Road region, increased from 0.26 in 2000 to 0.29 in 2015. Another one shows the proposed human comprehensive intensity indicator, which is about 78% of natural heritage sites was affected by human disturbance gradually during 1993 to 2016. This indicator is mainly, in fact, from the investment. So, in fact, we can still put more remote sensing data to monitor this cultural heritage. The next one is monitoring disaster loss reduction and the promotion of sustainable development in vulnerable areas in China. This one, for the disaster loss, the data mainly comes from national statistics, because we cannot say remote sensing can do everything. Sometimes the disaster loss related to population to economic comes from the statistics. So China has made a significant improvement to reduce the disaster loss in both economic loss and population loss. For the post-disaster recovery, we also use remote sensing data in high resolution to monitor, to find the plan of the rebuild region. For example, after the earthquake. Yeah. The next one is the monitoring and analyzing the particulate matter 2.5 in China. Here we produce this China's annual average PM 2.5 data products annually from 2010 to 2018, based on Moody's AOD and Moody's NDVI data in time series, and also some data from ECMWF. And also we do some population weighted calculation, because the population exposure is the main focus of the PM 2.5 pollution. So we can see in China, the Beijing, Tianjin, Hebei, Yangtze River Delta, and the Pearl River Delta, and the Chengdu, Chongqing regions showed an overall decreasing trend during 2010 to 2018. As you know, China has invested big financial service to reduce this negative impact from PM 2.5. And also, we do some work on open public space area in cities in China. For this one, we first make some definition of public open space, also include green spaces and parks, plazas, roads. We used POI data and some navigation data, kind of vector or raster data, and to use GIS technology and with high performance computing to extract this open space area. It shows that the share of open public space in built up region in Chinese cities were around 18% in 2015, and comes to 19.5 in 2018 respectively. So it shows it was improved gradually. Okay. Another very important issue is after we have this individual indicator, we need to make a comprehensive assessment of whole SDG 11. At the provincial scale here shows the result. We put all the indicators together and make some dashboard to indicate this province is on a positive change trend or a negative one, which means offset from the sustainable development. So most of it shows the rising or balanced trend. So yes, so this kind of indicator, the result can be used to provide some suggestions to our government to let them know which region need to be improved on the policy level. So that's the second part. The third part is about mapping high-resolution global imperial surface product. This one actually belongs to SDG 11.3, which means by 2030, enhance inclusive and sustainable urbanization and capacity for participatory, integrated and sustainable human settlement planning and management in all countries. This is the target. For the specific indicator, it is the ratio of land consumption rate to population growth rate, which belongs to Tier 2, which means it has the methodology, but still lack data globally. So our work is just focused on this indicator. We try to use the Sentinel Landsat data to produce 10 meters data globally. Here, we first calculated the population growth rate and also the land consumption rate. Then we divided the land consumption rate divided by population growth rate. We get a LCR, PGR, which indicate the speed, the comparison between land consumption rate and the population growth rate. In fact, this methodology was proposed by UN Habitat and UNEP. It's a standard methodology, but all the time it lacks data. Here are some global data in 2015 and 2018. As you know, this impervious surface area is a very small population proportion in the land cover. So for your direct impression, it accounts little. But let's see some detail. Here is a kind of distribution of the Eastern China. So the 10 resolution data can monitor this urban expansion in a very detail. For now, we do it in 2015 and 2018. Now we also start to do 2021. And here is the comparison between our high GISA data and some other data in the world, such as Gaia or from GLC or GHSL or NUACI, just some other data. We make some comparisons in some cities. The left one is our data. The fourth one on the left, on the right is the other product. So we can see the on the whole, it shows a similar pattern, but our data, because we use 10-meter resolution data, so it can get more detail. And we also do some accuracy validation globally for using some blocks in a random way. Our overall accuracy is 88%. And it has a slight difference in different continents. And here we make the accuracy validation between our data and the reference data, and also the other global data with the reference data. The right one, the one on the right is our product. We can see the R square tends to be 0.8%, which is higher than other product. The one in 2015 and the one in 2018, almost very similar result for R square. And our monitor result shows that the total area of global impervious surface in 2018 is around 1.29 million square kilometers, an increase of 20,000 square kilometers from 2015. And it also shows that Africa and South America has some slight faster growth rate. And of course, Asia accounts for 46%, and followed by Europe and North America and Europe. And also we show that the top 20 countries in terms of impervious surface area of the global in total. The top 3 are China, US, Russia, followed by India, Brazil. And here is the different the summed result from the different products. We can see that high GISA product is has a similar distribution with global land 13, because our data 10 meters, their data 30 meters. So they are close, they have close distribution. But for the data on the bottom, we know they are in coarse resolution. So some detailed impervious area has not been detected in such a coarse resolution. So they have a much lower value. The next one is our application to assess urban sustainability. Again, let's come to this SDG 11.3.1 indicator, which is the ratio of land consumption rate to population growth rate. For this research, the objectives are to extract this ISA data for 433 Chinese cities with more than 300,000 people from 1990 to 2015, and convert this ISA to the standard built-up area product. These two are different. We need to do the data conversion. And after that, we monitor and assess urban progress during this period. We employed a range of spectral indices from remote sensing to generate this SA maps for 433 Chinese cities. Many of them are remote sensing data, such as Landsat 5, 7, and Sentinel-1, synthetic aperture radar image, and also surface reflectance images, and some urban extended polygons, administrative areas, and the crowdsourced geospatial data, such as the OpenStreetMap. Using this big data, we generate this product. This one indicates that I mentioned before, the data conversion from ISA to built up area region. We developed this, we improved this technology based on UN Habitat. Here are some details. And also we have a paper on this. If you want to get more detail, you can find the paper on big Earth data recently. We compare our results with other data sets derived from National Bureau of Statistics of China and also UN Habitat. We can see our remote sensing data can help basically consistent with the national statistics, and also they are also close. But for UN Habitat data, we have some differences. We think it may result from the revolution difference of the data from UN Habitat. For the right chart, you can see similar spatial patterns also detected with the World Bank data. So here, for another, besides LCR, PGR, we think that except for land consumption and population consumption, we also need to put economic growth rate here related to land consumption rate, which we call it EGR LCR, which enables the quantitative estimation of coordination between land and economic growth. So here, the two charts shows that the rise in LCR PGR was paralleled by a decline in EGR LCR over the past decades in general for China. That means the land development rate are much faster than population growth rate and economic growth rate. And here, according to the overall trend, our main finding is that the northeast China, you can see their LCR PGR has showed a dispersed way, which indicates the unbalanced situation between land and population. And also the spatial expansion of super large cities in the central China may also get out of control. For EGR LCR, also the northeastern region remained about in an unbalanced way during the monitoring period, except 2010 to 2015. It indicates that the cities of different urban sizes in northeast China may have suffered a more severe economic downturn than other regions during this period. This one shows the changes in LCR PGR and EGR PGR for different function types over China, and also for different income groups. it shows that the resource-dependent cities faced several challenges for more effective actions of both economic transformation and population migration, while the gap of land use efficiency indicators of LCR, PGR, and EGR, LCR between different income groups of China's cities have been narrowed between 1990 and 2015. As you see, the right chart, there's so little difference, but on the left, it shows big difference. Another issue is that we also apply this methodology at a selected province in China, which is Hainan in southern China. We connect the Hainan, the cities and the county level data for 6 SDG 11 target from using remote sensing and local statistics and field data to assess the 18 counties and cities in Hainan province. We also do the dashboard for each county at county level for single index and also for their trend. We found that Haikou and Sanya had a stable ranking in each index, especially for the passenger volume and solid waste. And some cities or counties such as Changjiang and Ledong had the red indicators, so it should be noticed by their government. This one was recently published in Sustainability. And the level, we also do some comprehensive assessment to see the level of sustainable urbanization in Hainan province has been increasing year by year. And it has a spatial distribution pattern, which shows that development was high in the north and the south, but low in the central and the western regions. And Haikou as the administrative center and Sanya as the tourism center had the highest levels of sustainable development. Another issue is we also try to use the mooring index to assess the spatial autocorrelation of at the county level for Hainan province. So this indicator can detect the hotspot area of urban sustainability in Hainan province. It can detect high or no high and high-no regions for the urban sustainability index. Here the result shows that the overall Morris I of Hainan province was no, and it means that it did not have a comprehensive effect between or among the adjacent counties or cities. From 2011 to 2013, the urban agglomerations in Hainan province led by Ledong County and some other cities showed no cluster, a high no cluster. It means that these cities had a negative impact on their surrounding areas. For high cluster category, it lies in Sanya city in 2018. So as you know, the development of Sanya city drove the development of surrounding counties. It has some positive spillover effect. But overall speaking, the integrated development still have not been formed for Hainan province. So here, the next part is about conclusions. We has done many national cases and also done some started to done some local studies at the provincial level to monitor the progress of SDG 11 indicators and also make some assessment. And our this part also be included in this SDG bigger data in support of sustainable development goals report, which now we will release it at the United Nations General Assembly annually. Overall speaking, the methodology and this project, the main focus is to try to use different kind of remote sensing or spatial data or statistic data to fill in much of the SDG data gap and try to improve SDG whole assessment. So we see it has a great potential to sustainability science, which can bring great value and potential for monitoring and assessing SDG indicators. But of course, as you know, besides data for SDG, we still need to focus to care about its implementation. That means besides data, we still find solutions to each SDG. So we need try to attempt to put science and technology and also policy makers together to find solutions and also fill the data gap so that we can provide useful policies, suggestions to the government or to United Nations. Okay, that's all. Thank you.
Okay, thank you very much, Dr. Xing. That is very interesting and a lot of information, a lot from the SDG 11, a lot of indicator that you have access and your team has access. Yeah, so it's very, as I said, it's very informative and a lot of information. And thank you for sharing this kind of information on both local scale and also on the global scale. I think it will be benefit to all of us, especially the one that working on the measuring the progression of the SDG indicators. Also, I would like to maybe address your final conclusion again. We are doing this kind of the scientific research in order to monitor the SDG. But another component which also very important is how to bring this kind of information into the policy maker and make that as maybe the policy that will be finally benefit to our country, right? So I think maybe that leads to the first question that we have. I think it's very important here that, so the first question is, there are lots of analysis and product that in the term of regional and globally that you present. How can the policy maker and also the researcher who are interested in this kind of data will be able to access whether this information can be shareable in any platform or something like that?
In fact, most of the data can be downloaded openly from internet. Our 10-meter data now, I think we start maybe we are starting to develop the data sharing platform. Yes, then you can register, then you can apply for it. And I think in this year or the next year, I think we will also put it in open, because we are trying to give to United Nations first, then start to open. Yes. it is 10 resolution, but I think for 30 meters, we can download it from internet. You can search it in Google. Yeah, I think it's easy to find.
Yeah, okay. I think maybe the organizer will follow up with you and then maybe put the link or something like that, so
Okay.
that the interested researcher and maybe the government that would like to maybe have this kind of information can be follow up. Okay.
Okay.
Yep. Thank you. The second question is, so this kind of information, so can the land use projection be anticipated based on the SSP, the shared socio-economic pathway of IPCC AR6? So which that one reflect the different land use pattern in relation to greenhouse gas emission activity. So this will be interesting research and also useful for the land use policy maker. So what's your opinion about that?
Yes, now we are having a 5 year, from every 5 year we do the product. So I think from 1990 to 2015. So we now 5 terms global data. So I think it's possible to make some prediction toward the 2030, like SDG agenda. Yes, you can introduce a different kind of scenario or climate change to predict the land use pattern or the urban planning. I think it's possible.
Yeah. Okay, thank you. So it's like you developed the methodology in order to identify or link between the changes in the land use and also the greenhouse gas and so on.
Yeah.
And then later you can apply to different time scale, right?
Yeah.
Yeah, very nice. Okay, the next question is how do you define the Qiang tiles and identify and also distinguish Qiang tile between eastern and western of China by using the remote sensing image, as they might have different characteristics?
In fact, yes, but I think the most important is the spatial resolution of the data. As I introduced, we use the Chinese Gaofen satellite, Gaofen 2 satellite, which I think is around a meter resolution. So it is even in western part, the shanty towns or may become small, but 1 meter resolution, I think it's enough to detect the data. But the main problem sometimes is the cloud impact, and also we can. The most important, I think, is the data. Yeah.
Yep.
If your
Okay.
spatial resolution is enough, I think yes, for western part it also can be done.
Yeah. Okay. So I think when you present about the Qiang tile, I would like to discuss about this a little bit. It's really interesting that you said that you use also the AI or machine learning, right?
Yeah.
So what kind of the AI or machine learning tools that you apply in this application?
We sometimes because this one was done by another team. Yeah, but they participate in this SDG 11 project. I think they use some Google Earth engine, and some deep learning method on that platform, and also some TensorFlow, some FishNet or CNN, random forest. Such normal, I think it's a normal AI technology now commonly used. They didn't develop their own network.
Yeah. But I think to combine different technology together, that will also contribute to some of the methodology that we can use and also apply to other country or other location, right? Because if you use the tools that are already available, then we can apply the same tools with different location, and then that will be very interesting for other location too.
Yeah.
Okay, next question. What is your standard to choose the SDG indicators and the sub-indicators for assessing urban sustainability, as there might have not only one indicators?
Yes, as I mentioned, this one comes to United Nations definitions. It proposed 7 indicators for SDG 11. But in fact, it is not enough. But this 7 one, I think it's United Nations focus on. It try to serve as a framework to promote the policy makers to value these 7 aspects. But I mentioned for SDG 6, the water and the sanitation, and also the maybe from social point, the equality or gender equality or some consumption and production for SDG 12, they are all in fact closely related to urban, and for some economic growth SDG 8, and also renewable energy for SDG 7. They are all very closely related to urban. So if we want to assess urban SDG 11, then we can use these indicators. But if we want to make a full urban accessibility, I think still need to incorporate more indicators. Maybe you go through the over 200 indicators and find the closely related one, then make a full assessment.
Yeah, it's very interesting. So I think when you present the study in Hainan province, right, you have a list of maybe 6 SDG 11 target or something like that, and then you have really good or bad or something like that. Is it possible to prioritize some of the target? Because right now you have list of 6 indicator, maybe I don't know, maybe some of the policymaker would like to see the rank that maybe one number that, okay, these are the cities that they need to work on it first or something like that. It is in your idea, whether it's possible to maybe weighting some of the indicator and then have maybe final number as the number that can be judged that, okay, this one is the worst, this one is the better or something like that in terms of overall SDG 11 in different locations.
Yes, the weighting technology, yes. That in fact, they are also been on the research agenda for UN scientists. And they have made some PCA weighted technology or some other statistic weighted. But they, after testing, they come to the original. Because SDG, when it proposed, it says all the targets should be equally treated. So they comes to treat this each indicator in a balanced way. But in fact, yes, it is right. The different indicators or goals have different performances. It has the weight, but during the calculation, now the most of them just use 111 for each one, because they think each one are all equally important to urban sustainability.
I also agree with that. Yes. So this question may be to my interest. So I'm also working with PM 2.5, and then when I see the slide of PM 2.5, then it really strikes to me. So you're talking about the satellite MODIS, right? Are there any other satellite that your team also using in order to assess the PM 2.5 concentration in the city?
I think maybe the other data comes from the reanalysis data or the field station data more. For remote sensing data, I think currently most we use is MODIS because it has 36 channels, many are sensitive to atmosphere. But for other sensor or satellite, it has little. Normally, the optical, the radar didn't sensitive enough. And I think there are more now many open data also for this product.
Right. So I think it's also very nice that we have the same satellite that we use so that we can compare the data from different locations. So I think that's one of the benefits that we have using the same satellite. Yeah, I think I have another question in the list. Okay, so from the chat, I think this one is interesting. So you show a lot of your team work with a lot of indicators. So can you share with us which indicator that you can maybe consider as the biggest challenge in order to apply the big Earth data to measure that SDG progression?
You mean SDG 11 or whole SDG?
For the SDG 11 that you present of the result today, like which one is the biggest challenge for your team?
I think for the Shati town, now we just do 27 cities because the data restriction, as you know, for the high resolution data. Yes. So, and also for the public open space, sometimes it is difficult to find data earlier. Now we just do in 2010 or after 2010. Before, I think there was a little POI data or some other data.
Right.
Yeah, and also for the statistical data, I think it's okay. But when you come to the subnational level, such as the province county level, I think for the statistical data is also a challenge because at the county level, it is hard sometimes not enough statistic data. Yes, because this SDG 11, I think we cannot just only use remote sensing data.
Right.
Yeah.
Okay. Yeah, I think I would like to maybe thanks again, Dr. Xing, in order to give a very nice presentation and also address all of the comments from the audience. I would like to maybe this will be wrap up our session, but I would like to maybe invite Dr. Alan Tabukanon for the closing remark. Dr. Alan, to you, please.
Kind introduction. I hope everyone can hear me well. So first of all, on behalf of Mahidol University, we would like to pay the sincere appreciation to the National Research Council of Thailand, NRCT, as a funder, and the most important is the Chinese Academy of Science, Asian Institute of Technology, AIT. Without all of this, the event can't be possible and not be successful. And we are talking about a lot of SDG 2, 6, 11, 13, 14, 15, or other else. But what we are doing now is SDG 17 partnership. Because now, without any partnership, we can't achieve any SDG, right? We have to work together, researcher, government, local people, and also the country, international countries, to jointly achieve the goal together. It's the global goal, not the national goal, right? So what we are doing now is also SDG 17. So what I have learned from these 2 days, I would like to express my appreciation again to Dr. Jun Cheung Lee, Dr. Lee Jung Xiu, Professor Haifeng Gu, and Dr. Qiang for very informative and very advanced knowledge for Thai people and other country people. So I am looking forward to continuing the collaboration, and what we are thinking is that we can develop some course like big Earth data coursework, maybe with the joint implementation among the CAS, AIT, and Mahidol University. We can develop some big Earth data course for monitoring SDG goals. I hope that will be very useful and will be very interesting for many people, not only for Thai people. So I encourage for further discussion on this possibility. And we hope that we have chance to meet you, all of you again, face to face in either Thailand or China, to have more further and fruitful discussion. I would love it. I visit China many times, so I like China very much, especially food. So I hope I can be back there soon. So thank you very much, everyone, for participation and kindly joining this event. Thank you very much.